Gravity is the first law of physics we ever experience, long before we know what physics is, before we can speak, before we can count, before we can form memories that last. Gravity is already teaching us its rules. It pulls toys from our hands. It keeps our feet on the floor. It reminds us, sometimes painfully, that jumping off high places has consequences. And because gravity is always there, always consistent, always doing the same thing day after day, it feels obvious, almost boring. We think we understand it because we live inside it. But that sense of familiarity is exactly why gravity is so deeply misunderstood. Hi there, and welcome to Sleepy Space Traveler. I'm really glad you're here, and I hope this moment can become a pause in your day. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from and what time it is for you right now. Thank you for being here. Now, let's begin. Among all the forces known to science, gravity is the one we rely on the most and understand the least. It shapes the motion of planets, the formation of stars, the structure of galaxies, and the evolution of the entire universe. It controls the flow of time itself. And yet, when physicists try to describe what gravity actually is at its deepest level, they still argue, disagree, and admit uncertainty. This video begins with a simple idea. Gravity feels simple because it hides its true nature behind everyday experience. Once we step back and look at gravity not as something that makes objects fall, but as something that shapes reality itself, it quickly stops making intuitive sense. For most of human history, gravity was explained using common sense. Heavy things fall down. Light things fall slower. Objects move toward their natural place. These ideas were not foolish. They were reasonable interpretations of daily life. If you drop a stone and a feather, the stone hits the ground first. That seems like clear evidence that gravity pulls harder on heavy things. This view dominated ancient thinking for centuries, most famously through the ideas of Aristotle. According to this perspective, the universe had a natural order. Earth was at the center. Heavy objects belonged near it. Fire rose upward. Everything had a preferred direction. Gravity was not a force so much as a tendency, a desire of objects to return to where they belonged. The problem was not that this idea was lazy or irrational. The problem was that it relied entirely on what humans could observe with their senses. And human senses are terrible at understanding forces that act everywhere, all the time, equally on everything. The first major crack in this way of thinking came with a realization that seems obvious now, but was revolutionary at the time. Objects fall at the same rate when air resistance is removed. Drop a feather and a stone in a vacuum, and they hit the ground together. Gravity does not care about mass in the way Aristotle imagined. This realization paved the way for Isaac Newton, whose work transformed gravity from a vague tendency into a precise mathematical rule. Newton proposed that every object with mass attracts every other object with mass. The force depends on how massive the objects are and how far apart they are. Double the mass, double the pull. double the distance, and the force drops dramatically. For the first time, gravity became something that could be calculated. The same equation that described an apple falling from a tree could also describe the motion of the moon around Earth and the planets around the sun. This was astonishing. It suggested that the heavens were not governed by different rules than Earth. The universe followed one set of laws everywhere, and for centuries, Newton's gravity worked beautifully. It predicted planetary motion with incredible accuracy. It explained tides, orbits, and trajectories. It allowed engineers to design bridges and astronomers to chart the skies. Even today, most space missions rely heavily on Newton's equations because they are simple, reliable, and precise enough for most purposes. But there was a problem hiding in plain sight. Newton's gravity described how objects move, but not why gravity exists at all. It required what physicists call action at a distance. The sun somehow pulls on Earth across empty space. Earth somehow pulls on the moon without touching it. No mechanism was provided. Gravity simply acted. Newton himself was uncomfortable with this. He famously admitted that he did not know what caused gravity. He had described its behavior, not its essence, and for a long time, that distinction did not seem to matter. If the math worked, why worry? The trouble is that gravity behaves very differently from other forces. Electromagnetism, for example, acts through fields that can be measured and blocked. Charges can repel as well as attract. Gravity only attracts. There's no gravitational repulsion in everyday physics. There's no gravitational shielding. You cannot block gravity with a wall. Even more strangely, gravity affects everything equally. In a vacuum, all objects fall at the same rate regardless of mass. That fact alone hints that gravity is not acting like a typical force pushing or pulling objects directly. Something deeper is happening. This mystery deepened when scientists began to understand motion more carefully. Imagine floating in deep space, far from stars or planets. You feel weightless. Now imagine falling toward Earth. You also feel weightless. That seems strange. Falling feels very different from floating, doesn't it? Yet, from the perspective of physics, these two situations are identical. In both cases, you are not experiencing any force acting on your body. You are simply moving along a natural path through space and time. This insight leads directly to one of the most important ideas in modern physics. Gravity is not what makes things fall. Falling is what happens when nothing prevents motion. Standing on the ground feels normal, but from a physical perspective, it is the unusual situation. The ground pushes up on you, preventing you from following your natural path. That upward push is what creates the sensation of weight. Gravity is not pulling you down. The ground is pushing you up. This idea sounds like a trick of words, but it leads to a profound shift in how gravity is understood. It suggests that gravity is not a force in the usual sense. Instead, it might be something about the structure of space and time themselves. This is where Albert Einstein enters the story. Einstein approached gravity not as a force, but as a problem of motion. He asked a simple but radical question. What if objects in free fall are not being pulled at all? What if they are simply moving naturally through a curved space-time? To understand this idea, forget gravity for a moment and think about geometry. Imagine walking across a flat field. The shortest path between 2 points is a straight line. Now imagine walking across a curved hill. The shortest path bends. You are not being pushed sideways. The surface itself guides your motion. Einstein proposed that mass and energy bend spacetime in a similar way. Objects move along the straightest possible paths in that curved spacetime. From our perspective, those paths look like acceleration, orbit, or falling. But nothing is being pulled. Objects are simply following the shape of reality. This idea became the foundation of general relativity, and it completely replaced Newton's concept of gravity. Gravity was no longer a force acting within space and time. It was the shape of space and time. This explains why gravity affects everything equally. It is not pushing on objects differently based on mass or composition. It is shaping the paths that all objects must follow. Light bends near massive objects, not because it has weight, but because spacetime itself is curved. General relativity also explains why gravity affects time. Clocks run slower near massive objects because time itself is part of spacetime. When spacetime curves, time stretches. These predictions were not philosophical guesses. They were tested and confirmed. Light bending around the sun was observed during a solar eclipse. Atomic clocks tick at different rates depending on altitude. GPS satellites must correct for gravitational time dilation, or they would fail within minutes. Despite its success, general relativity introduced new mysteries. It describes gravity on large scales beautifully, but it does not fit with quantum mechanics, the theory that governs the microscopic world. When physicists try to combine the two, the equations break down. This is where gravity becomes truly misunderstood. We have a theory that works incredibly well for planets, stars, and galaxies. We have another theory that works incredibly well for atoms and particles, but when gravity enters the quantum realm, our understanding collapses. Is gravity made of particles? If so, what are they? Is spacetime smooth, or is it made of tiny discrete pieces? Does gravity emerge from something more fundamental, like temperature emerges from particle motion? These questions remain unanswered, and yet gravity continues to shape everything. It binds galaxies into clusters. It forms stars from clouds of gas. It controls the expansion of the universe. It even played a role in the origin of time itself. Gravity is weak compared to other forces, but it is relentless. It accumulates. Over cosmic distances and timescales, it dominates. This first part establishes the central idea of the video. Gravity feels simple, but it is anything but. What we experience daily is just the surface of a phenomenon that reshapes reality, bends time, and governs the universe on the largest scales imaginable. In the next part, we will move deeper into how gravity sculpts motion, why free fall reveals its true nature, and how Einstein's insight completely reversed our everyday intuition about what it means to fall, stand, and move through the universe. Once we accept that gravity is not really a force in the everyday sense, but a consequence of curved space-time, a lot of familiar experiences begin to look strange in a productive way. Falling, orbiting, floating, standing still. These are no longer simple actions, but clues about the shape of reality itself. Consider orbiting. It feels intuitive to say that the moon stays in orbit because Earth's gravity pulls it inward, while its forward motion keeps it from crashing down. This picture is useful, but it hides what is really happening. From Einstein's perspective, the moon is not being pulled in and flung outward at the same time. Instead, it is moving along the straightest possible path through curved spacetime. The Earth bends spacetime around it, and the moon simply follows that bend. A helpful analogy is to imagine rolling a marble across a stretched rubber sheet. If the sheet is flat, the marble rolls straight. If you place a heavy object in the center, the sheet curves. Now roll the marble again. Its path bends, not because the marble wants to move inward, but because the surface itself is curved. The marble is obeying geometry, not responding to a force. This analogy is imperfect. Space-time is not a sheet, and it curves in 4 dimensions, not 2, but it captures the key idea. Motion is guided by geometry. Gravity is geometry. This perspective explains something that puzzled scientists for centuries: why inertial mass and gravitational mass are the same. Inertial mass measures how much an object resists acceleration. Gravitational mass measures how strongly an object responds to gravity. Experiments show these are always equal, to astonishing precision. In Newton's framework, this equality was a coincidence. In Einstein's framework, it is inevitable. All objects move along the same spacetime paths regardless of mass. The geometry does not care what you are made of. This is why astronauts orbiting Earth feel weightless even though gravity is still strong where they are. Gravity has not disappeared. They are simply falling freely, following spacetime's curve. The spacecraft, the astronauts, and everything inside are all falling together. With nothing pushing back, weight vanishes. Standing on Earth feels like rest, but in spacetime terms it is forced motion. The ground prevents you from following your natural path. The sensation of weight comes from the electromagnetic forces in the floor pushing up on your body. Gravity is not pressing you down. Matter is holding you up. This reversal of intuition is one of the hardest parts of gravity to truly absorb. It goes against how our brains evolved to interpret motion. But once understood, it becomes a powerful tool for thinking about everything from satellites to black holes. As scientists explored general relativity further, they discovered that gravity does more than curve space. It also stretches and compresses time. Near massive objects, time slows down. Far away, it speeds up. Then is not a metaphor, it is measurable. Atomic clocks placed at different altitudes tick at different rates. GPS satellites experience weaker gravity than clocks on Earth's surface, so their clocks run faster. Engineers must correct for this difference, or GPS errors would accumulate at kilometers per day. Time dilation due to gravity reveals something profound. Time is not universal. It depends on location and motion. The universe does not share a single global clock. This idea feels unsettling because human experience depends on shared time. We assume that now means the same thing everywhere. Physics tells us otherwise. Gravity also influences how light moves. Light always travels at the same speed locally, but its path can bend through curved spacetime. This effect, called gravitational lensing, allows astronomers to see distant galaxies whose light is bent around massive clusters. Gravitational lensing is not just a curiosity. It is one of the most powerful tools in modern cosmology. By measuring how light bends, scientists can map the distribution of mass, including dark matter, in the universe. Dark matter reveals another layer of gravity's mystery. Galaxies rotate faster than expected based on visible matter alone. Something unseen must be contributing extra gravitational pull. Either there is more mass than we can see, or our understanding of gravity is incomplete. Most evidence favors dark matter, an invisible form of matter that interacts gravitationally but not electromagnetically. But alternative theories modify gravity itself. These theories attempt to explain cosmic behavior without invoking unseen mass. The debate is ongoing. Gravity might be telling us about new particles, new fields, or new principles of spacetime, or all three. General relativity predicts extreme consequences when mass becomes very concentrated. When enough mass is squeezed into a small region, spacetime curves so sharply that not even light can escape. This creates a black hole. Black holes are not holes in space, but regions where spacetime curvature becomes extreme. The event horizon marks the boundary beyond which paths lead inevitably inward. Once crossed, all possible futures point toward the center. Near a black hole, time slows dramatically relative to distant observers. From far away, objects appear to freeze as they approach the horizon. From the object's own perspective, time continues normally, until tidal forces become destructive. These predictions were once considered mathematical oddities. Today, black holes are observed indirectly through gravitational waves, accretion disks, and stellar motion. They are not theoretical accidents. They are common features of the universe. Gravitational waves themselves represent another triumph of Einstein's theory. When massive objects accelerate, they produce ripples in spacetime that propagate outward at the speed of light. These waves stretch and compress space as they pass. Detecting gravitational waves required instruments capable of measuring changes smaller than an atomic nucleus across kilometers. When detected, they confirmed that spacetime itself is dynamic, capable of oscillation. Gravity is not just a background stage. It moves, vibrates, and carries energy. Despite these successes, gravity remains incompatible with quantum mechanics. Quantum theory describes forces through particle exchange. Gravity resists this description. If gravity has a quantum particle, it would be called a graviton. No graviton has ever been observed. Some theories predict they exist, but are extraordinarily difficult to detect. Others suggest gravity is emergent, arising from collective behavior of more fundamental components. One analogy compares gravity to temperature. Temperature is real, measurable, and powerful, but it is not fundamental. It emerges from the motion of atoms. Perhaps spacetime and gravity emerge from microscopic quantum information. Ideas like loop quantum gravity, string theory, and holographic principles attempt to resolve this conflict. None are experimentally confirmed yet. Each provides insight, but no final answer. What makes gravity uniquely challenging is its universality. It affects everything, everywhere, all at once. You cannot isolate gravity in a laboratory the way you can isolate electric charge. Gravity also shapes the universe's largest structures. Galaxies form where gravity pulls matter together. Cosmic voids form where gravity is weaker. The universe's large-scale structure resembles a web, with filaments and nodes shaped by gravitational attraction over billions of years. Even the expansion of the universe is governed by gravity and something else. Observations show that expansion is accelerating, driven by dark energy. Whether dark energy is a property of spacetime itself or a new field remains unknown. Gravity interacts with this expansion in subtle ways. On small scales, gravity dominates and binds systems together. On large scales, Expansion stretches space itself. This dual role makes gravity both a builder and a sculptor. It assembles matter into structure while participating in cosmic evolution. At this point, gravity appears less like a single phenomenon and more like a window into the deepest layers of reality. It connects motion, time, space, energy, and geometry into a unified picture. One that works astonishingly well but remains incomplete. The more precisely we measure gravity, the more it reveals its strangeness. Tiny discrepancies might point to new physics. Slight deviations could open doors to deeper understanding. In the next part, we will explore gravity's role in shaping the universe as a whole, how it governed the early cosmos, influenced the birth of structure, and continues to guide the universe's fate. When we zoom out from planets, stars, and black holes and look at the universe as a whole, gravity begins to feel less like a background rule and more like the main architect of everything we see. The universe did not begin as a neatly organized place filled with galaxies and cosmic structures. It began hot, dense, and remarkably smooth. And gravity was responsible for turning that smoothness into complexity. Shortly after the Big Bang, the universe was almost perfectly uniform. Matter and energy were spread out nearly evenly, with only tiny fluctuations in density. These fluctuations were incredibly small, differences of just 1 part in 100,000. Yet gravity amplified them over billions of years. You can think of the early universe like a calm lake with faint ripples. The ripples are barely noticeable at first, but gravity acts like a patent sculptor, slowly deepening them. Regions with slightly more matter pulled in even more matter. Regions with slightly less matter lost out. Over time, these small differences grew into the vast cosmic structures we see today. This process is known as gravitational instability. It is simple in principle, but powerful in outcome. Wherever matter clumps, gravity strengthens. Wherever gravity strengthens, more matter follows. It is a feedback loop that turns tiny imperfections into galaxies, clusters, and superclusters. Without gravity, the universe would still be a nearly uniform fog of particles and radiation. No stars, no planets, no chemistry, no life. Gravity is the reason complexity exists at all. As matter collapsed under gravity, it did not fall straight inward. Small motions and irregularities caused collapsing clouds to spin. This spinning motion flattened matter into disks, which is why galaxies tend to be flat and spiral-shaped rather than spherical. Angular momentum, once present, is conserved. Gravity pulls inward, but rotation resists complete collapse. This balance between gravity and motion explains why stars form inside rotating disks of gas, why planets orbit stars, and why galaxies develop elegant spiral arms. Gravity gathers matter, but motion shapes how it settles. On even larger scales, gravity creates the cosmic web. Galaxies are not randomly scattered through space. They trace filaments of dark matter, forming vast interconnected structures separated by enormous voids. Dark matter plays a crucial role here. Unlike ordinary matter, dark matter does not interact with light. It does not cool, collide, or form stars. But it exerts gravity. It forms invisible scaffolding that guides the motion of visible matter. Simulations show that dark matter collapses first, forming halos. Ordinary matter falls into these halos, heats up, cools, and eventually forms galaxies. Without dark matter, the universe would look very different. Galaxies would form much later, if at all. Gravity's role in cosmic evolution is therefore inseparable from dark matter. We do not yet know what dark matter is made of, but we know how it behaves gravitationally. Its presence is inferred from motion, lensing, and structure formation. This is one of gravity's most interesting qualities. It allows us to detect the invisible. By observing how things move and bend light, we can infer the existence of matter we cannot see. Gravity also governs the life cycles of stars. A star begins when a cloud of gas collapses under gravity. As it collapses, temperature and pressure rise until nuclear fusion ignites. Fusion pushes outward, balancing gravity's inward pull. For most of a star's life, gravity and pressure exist in equilibrium. When fusion fuel runs low, gravity regains control. The star collapses further, sometimes gently, sometimes catastrophically. Low-mass stars shed outer layers and leave behind white dwarfs. More massive stars collapse violently, triggering supernova explosions and forming neutron stars or black holes. Gravity decides the outcome. In neutron stars, gravity compresses matter to extreme densities. Atoms collapse, electrons combine with protons, and matter becomes a sea of neutrons. A teaspoon of neutron star material would weigh billions of tons on Earth. In black holes, gravity overwhelms all known forces. Matter collapses beyond any known state, forming a singularity where our current theories break down. Gravity pushes physics to its limits. Even outside extreme objects, gravity subtly shapes everyday phenomena. Ocean tides are caused by the moon's gravity stretching Earth slightly. The same principle applies to galaxies interacting and merging. When galaxies pass near each other, gravity distorts their shapes, pulling out long tidal tails of stars and gas. Over time, galaxies can merge, forming larger systems. These mergers play a major role in galaxy evolution. The Milky Way itself has grown through mergers. It continues to absorb smaller galaxies. In a few billion years, it will merge with the Andromeda Galaxy, reshaping both. Gravity operates on timescales far longer than human history. Processes unfold over millions or billions of years. Yet the underlying rules are simple and consistent. One of gravity's most puzzling aspects emerges when we look at the universe's expansion. According to general relativity, gravity should slow expansion over time as matter pulls everything together. For decades, this was the expectation. Then, observations revealed something unexpected. The expansion of the universe is accelerating. Galaxies are not just moving apart. They are doing so faster and faster. This acceleration implies the presence of dark energy, a mysterious component that acts like a repulsive form of gravity. Dark energy does not pull matter together. It pushes spacetime apart. From one perspective, dark energy might be a property of empty space itself. In Einstein's equations, this appears as the cosmological constant. Empty space has energy, and that energy influences spacetime's behavior. From another perspective, dark energy might be a dynamic field that changes over time. Or it could signal a breakdown of general relativity on cosmic scales. Whatever its nature, dark energy dominates the universe's energy budget. Ordinary matter makes up only about 5%. Dark matter contributes about 25%. Dark energy accounts for the rest. Gravity interacts with all of these components. On small scales, gravity wins. Galaxies remain bound. On large scales, dark energy dominates, driving accelerated expansion. This creates a strange cosmic hierarchy. Gravity is powerful locally but weak globally. It binds planets, stars, and galaxies, yet it cannot overcome the universe's accelerating expansion. This balance determines the universe's ultimate fate. If dark energy remains constant, distant galaxies will eventually recede beyond our observable horizon. The universe will grow colder, darker, and more isolated. If dark energy increases, expansion could tear apart galaxies, stars, planets, and even atoms in a scenario known as the Big Rip. If it decreases or reverses, gravity might eventually cause the universe to collapse again. These possibilities depend on how gravity behaves at the largest scales. Tiny differences in equations lead to dramatically different futures. What makes gravity especially difficult to understand here is that it behaves differently depending on scale. Newton's gravity works beautifully for everyday objects. General relativity works for stars, black holes, and cosmology. But quantum mechanics governs particles and forces at tiny scales. Gravity resists quantization. Attempts to describe gravity as a quantum force lead to infinities and inconsistencies. This suggests that gravity might not be fundamental in the same way as other forces. Some theories propose that spacetime itself emerges from quantum information. In this view, gravity is a statistical effect, similar to pressure or temperature. It arises from the collective behavior of microscopic degrees of freedom. One analogy compares space-time to a fluid. At large scales, it behaves smoothly. At small scales, it may have a granular structure. Gravity emerges from this structure rather than existing independently. Another analogy compares gravity to elasticity. Space-time resists deformation, and curvature is its response. This resistance is encoded in Einstein's equations. These ideas are speculative, but they reflect a growing sense that gravity is deeply tied to relational structure rather than force exchange. The fact that gravity governs both cosmic evolution and everyday experience makes it uniquely important. It connects the largest scales of the universe to the smallest moments of human life. When you stand on the ground, when the moon orbits Earth, when galaxies form and merge, when the universe expands, the same underlying principle is at work. Yet gravity remains the least understood of the fundamental interactions. We can calculate its effects with astonishing precision, but we do not fully understand its origin. In the next part, we will turn our attention to gravity's relationship with energy, pressure, and momentum, and explore why gravity does not always attract, and how this counterintuitive behavior reshapes our understanding of the cosmos. One of the most counterintuitive things about gravity is that it does not only respond to mass. In Einstein's description of gravity, everything that carries energy influences space-time. That includes pressure, momentum, and even stresses inside matter. This idea feels strange because in everyday life we associate gravity with weight, with how heavy something feels. But in the universe at large, gravity cares about far more than just how much stuff there is. A simple way to picture this is to imagine space-time as a flexible fabric, but instead of being pressed down only by heavy objects, it responds to anything that contains energy or motion. A fast-moving particle curves space-time. Hot gas curves space-time. Even light, which has no rest mass, curves space-time because it carries energy and momentum. This is not just theoretical elegance. It has real, measurable consequences. For example, Light passing near the sun bends slightly. This bending was first observed during a solar eclipse in 1919 and provided dramatic confirmation of general relativity. Newtonian gravity could not explain why massless light would curve. Einstein's gravity could. Another consequence is that pressure itself contributes to gravity. In extremely dense environments like neutron stars, pressure becomes so intense that it adds significantly to the star's gravitational pull. Pressure is not merely something resisting collapse, it is part of what curves spacetime. This leads to an unsettling realization. In extreme conditions, gravity can feed on itself. Energy creates gravity, gravity compresses matter, compression raises energy density, and that increased energy strengthens gravity further. This runaway process is what leads to black hole formation. Even in less extreme cases, this interplay shapes cosmic evolution. The early universe was filled with hot, dense plasma. Pressure was enormous. That pressure affected how spacetime evolved, influencing the rate at which the universe expanded. As the universe cooled and expanded, pressure dropped. Matter began to dominate gravity's behavior. Later still, dark energy emerged as the dominant influence. Gravity's role shifted again. This shifting balance explains why gravity cannot be thought of as a single, simple force, acting the same way everywhere and always. It is deeply context-dependent. Another idea that challenges intuition is that gravity does not transmit instantly. Changes in gravitational fields propagate at the speed of light. If the sun were to disappear, an impossible scenario but a useful thought experiment, Earth would continue orbiting for about 8 minutes before feeling the change. This finite speed means gravity carries information. Gravitational waves are ripples in spacetime produced by accelerating masses, such as merging black holes or neutron stars. These waves were predicted by Einstein a century ago and detected directly only recently. Gravitational waves are not distortions moving through space. They are distortions of space itself. As a wave passes, distances stretch and squeeze slightly. The effect is incredibly tiny, far smaller than the width of an atomic nucleus, yet detectable with sufficiently precise instruments. The detection of gravitational waves opened a new way of observing the universe. Instead of seeing cosmic events through light, we can now feel them through spacetime vibrations. This has confirmed that gravity behaves exactly as general relativity predicts, even in the most violent environments. These waves also reinforce the idea that gravity is not a force acting across space, but a dynamic feature of spacetime itself. Objects do not pull on each other through an invisible tether. They move along paths shaped by spacetime geometry. This geometric view helps explain why gravity affects everything equally. In a gravitational field, all objects fall at the same rate, regardless of mass. This is because they are all following the same spacetime paths. This principle, known as the equivalence principle, lies at the heart of general relativity. It tells us that there is no local experiment that can distinguish between uniform acceleration and a gravitational field. In everyday terms, this is why astronauts in orbit feel weightless. They are not beyond Earth's gravity. They are constantly falling around Earth, following curved spacetime paths that keep them in orbit. Gravity, then, is not something you feel directly. What you feel is resistance to gravity, such as the ground pushing up against your feet. remove that resistance, and gravity becomes invisible. This perspective also explains why gravity is so difficult to reconcile with quantum mechanics. Quantum theories describe forces as exchanges of particles. Gravity does not fit neatly into that framework because it is not acting within spacetime. It defines spacetime. Attempts to describe gravity as a particle-based force introduce a hypothetical graviton, but such a particle has never been detected. Even if it exists, it may not capture the full story. Some physicists suspect that gravity is emergent rather than fundamental. In this view, spacetime and gravity arise from deeper quantum processes, much as temperature arises from the motion of molecules. You do not need a fundamental temperature particle to explain heat. Similarly, you may not need a fundamental gravity particle to explain curvature. Gravity could be a macroscopic effect of microscopic degrees of freedom. This idea is supported by surprising connections between gravity, thermodynamics, and information theory. Black holes, for example, have entropy. They have temperature. They obey laws that resemble thermodynamic laws. A black hole's entropy is proportional to the area of its event horizon, not its volume. This suggests that information about what falls into a black hole is stored on its surface, not inside it. This observation led to the holographic principle, which proposes that all the information in a volume of space can be described by data on its boundary. In this view, our three-dimensional universe might be encoded on a distant two-dimensional surface. While this sounds abstract, it has produced concrete mathematical results. Certain quantum theories without gravity can be shown to be equivalent to gravitational theories in higher dimensions. These dualities hint that gravity might be a manifestation of how information is organized. Space-time curvature could reflect patterns of entanglement in an underlying quantum system. If this is true, gravity is not merely misunderstood. It is deeply entwined with the nature of reality itself. Even without resolving these deep questions, gravity's influence on structure formation remains clear. Gravity gathers matter, but it does so inefficiently. It is the weakest of the fundamental interactions. This weakness is why stars burn for billions of years instead of collapsing instantly. It is why planetary systems are stable. It is why life has time to develop. If gravity were slightly stronger, stars would burn faster. If it were slightly weaker, stars might never ignite. The universe would look radically different. This sensitivity has led some to suggest that gravity's strength is finely tuned. Whether this tuning is accidental, necessary, or evidence of deeper principles remains debated. Regardless of interpretation, gravity's gentle persistence shapes everything over time. It is slow but relentless. One way to appreciate gravity's long-term influence is to consider orbital decay. Gravitational waves carry energy away from orbiting systems. Over immense timescales, this causes orbits to shrink. Binary neutron stars spiral together and merge. Planets slowly drift. Even Earth's orbit is not perfectly stable forever. These changes are tiny on human timescales, but profound over cosmic ones. Gravity sculpts the universe patiently. As we move forward, the next challenge is understanding how gravity behaves when combined with quantum uncertainty. In regions like black hole interiors or the universe's earliest moments, both gravity and quantum mechanics are essential. Our current theories cannot fully describe such regimes. Something fundamental is missing. In the next part, we will explore attempts to unify gravity with quantum physics, examine why these efforts are so difficult, and consider what success might reveal about the deepest structure of the universe. If gravity really is woven into the fabric of space-time, then the biggest mystery is what that fabric is made of at the smallest scales. This question becomes unavoidable when we push gravity into situations where quantum effects cannot be ignored. Black holes and the early universe are not just extreme environments. They are testing grounds where our best theories stop working. Quantum mechanics governs the behavior of particles at tiny scales. It describes uncertainty, probabilities, and discrete packets of energy. Gravity, as described by general relativity, is smooth, continuous, and geometric. When physicists try to combine these frameworks, the mathematics breaks down in troubling ways. One way to see the problem is to imagine spacetime itself becoming subject to quantum uncertainty. In quantum mechanics, nothing can have both perfectly defined position and momentum. If spacetime is made of something, then its geometry should fluctuate at small scales. But general relativity assumes spacetime can be arbitrarily smooth. At scales near the Planck length, about 10 trillion times smaller than a proton, spacetime may no longer behave like a smooth surface. It may resemble a foamy structure, full of fluctuations and microscopic distortions. Trying to calculate gravitational interactions at these scales leads to infinities that cannot be removed using standard techniques. These infinities are not just mathematical inconveniences. They indicate that the theory is incomplete. This is why gravity is often described as the odd one out among the fundamental interactions. The electromagnetic, weak and strong forces fit neatly into the quantum framework. Gravity refuses to cooperate. One approach to this problem is to quantize gravity directly, treating spacetime curvature as something that can exist in discrete units. This leads to the idea of gravitons, hypothetical particles that mediate gravitational interactions. In simple terms, a graviton would be to gravity what a photon is to electromagnetism. But gravitons, if they exist, would interact incredibly weakly. Detecting a single graviton would require an experiment larger than the observable universe. Even worse, when gravity is treated as a quantum field in the usual way, calculations spiral out of control. The theory becomes non-renormalizable, meaning infinities pile up faster than they can be cancelled. This has led many physicists to conclude that gravity cannot be quantized in isolation. It may need a deeper framework. String theory is one such attempt. Instead of point particles, string theory proposes that the fundamental constituents of nature are tiny vibrating strings. Different vibration patterns correspond to different particles. Remarkably, when gravity is included in string theory, a graviton appears naturally as one of the string's vibration modes. Gravity is not added by hand. It emerges automatically. String theory also requires extra dimensions of space. These dimensions are compactified, curled up so tightly that they are invisible at accessible energies. While this may sound speculative, string theory has produced deep insights into black holes, quantum gravity, and the relationship between spacetime and information. However, it has not yet produced testable predictions that distinguish it clearly from other approaches. Another approach is loop quantum gravity. Instead of starting with particles, it starts with spacetime itself. In this view, Spacetime is composed of discrete loops or networks at the smallest scales. Areas and volumes become quantized. There is a smallest possible unit of space, much like there is a smallest unit of energy in quantum mechanics. Loop quantum gravity predicts that singularities, such as those at the centers of black holes or the Big Bang, are replaced by finite, well-behaved structures. Gravity becomes repulsive at extreme densities, preventing infinite collapse. This idea suggests that the universe may have bounced into existence rather than emerging from a singular point. Before the Big Bang, there may have been a contracting universe. These ideas are mathematically consistent but remain difficult to test. Both string theory and loop quantum gravity face the same challenge. The relevant scales are far beyond experimental reach. Still, indirect clues may exist. Black hole thermodynamics, for example, offers a bridge between gravity and quantum mechanics. Black holes behave like thermodynamic systems. They have temperature, entropy, and obey laws resembling those of heat and energy. A black hole's temperature is inversely proportional to its mass. Smaller black holes are hotter. Large black holes are extremely cold. This temperature arises from quantum effects near the event horizon. Particle-antiparticle pairs constantly form near the horizon. Occasionally, one escapes while the other falls in, causing the black hole to lose mass. This process, known as Hawking radiation, shows that black holes are not truly black. Over vast timescales, they evaporate. Hawking radiation introduces a deep puzzle. If a black hole evaporates completely, what happens to the information about what fell into it? Quantum mechanics insists that information cannot be destroyed. If information is lost, quantum theory breaks. If it escapes somehow, our understanding of spacetime must change. This tension is known as the black hole information paradox. Resolving it has driven much of modern theoretical physics. One proposed solution is that information is encoded on the event horizon and released gradually through Hawking radiation. Another suggests that spacetime inside the black hole connects to another region of the universe. Some proposals go even further, suggesting that spacetime itself is emergent from quantum entanglement. In this view, entangled particles are linked by geometric connections, sometimes metaphorically called wormholes. The phrase ER equals EPR captures this idea, proposing a relationship between Einstein-Rosen bridges and quantum entanglement. While still speculative, this line of thought has reshaped how physicists think about gravity. Gravity may not be fundamental. It may arise from statistical behavior of microscopic degrees of freedom, much like pressure arises from molecular motion. This would explain why gravity is so weak. It is not a primary interaction, but an emergent one. If true, this would also explain why gravity resists quantization. You do not quantize temperature directly. You quantize the molecules that produce it. In such a picture, spacetime is not a stage where physics happens. It is a result of physics happening. This idea also connects gravity to information. Spacetime geometry might reflect how information is distributed and entangled. This would make gravity less about attraction and more about organization. Even without a complete theory, these insights already influence cosmology. In the early universe, quantum fluctuations in spacetime may have seeded the large-scale structure we see today. Tiny variations were stretched by cosmic expansion, becoming galaxies, clusters, and voids. Gravity amplified these variations, pulling matter into denser regions while leaving vast empty spaces. This process explains why the universe has structure at all. Without gravity, matter would remain evenly spread and nothing would form. The interplay between quantum fluctuations and gravity is one of the most successful ideas in modern cosmology. It also suggests that understanding gravity is essential for understanding why the universe looks the way it does. As we move forward, the question is not just how gravity works, but what it really is. Is it fundamental or emergent? Geometric or informational? Continuous or discrete? In the next part, we will explore gravity's role in shaping galaxies, dark matter, and the large-scale structure of the universe, and how our misunderstanding of gravity may be hiding some of the biggest discoveries still ahead. When we zoom out from quantum puzzles and return to the vast scales of the cosmos, gravity begins to behave in ways that are just as unsettling, but for very different reasons. On the scale of galaxies and galaxy clusters, gravity appears to be stronger than it should be. Stars orbit too fast. Galaxies hold together too well. Massive structures form and remain stable in ways that standard gravity, applied only to visible matter, cannot easily explain. This problem was noticed nearly a century ago. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster of galaxies and found that the galaxies were moving far too quickly to remain bound if gravity came only from the visible stars and gas. Something invisible had to be providing extra gravitational pull. He called it dunkle Materie, dark matter. At first, this idea seemed speculative, but over the decades, evidence accumulated. When astronomers measure how stars orbit the centers of galaxies, they find something strange. Instead of slowing down with distance, as expected from Newtonian gravity, orbital speeds remain nearly constant far from the center. This creates what are called flat rotation curves. Imagine swinging a ball on a string. If you shorten the string, the ball moves faster. If you lengthen it, the ball slows down. That is what gravity predicts for stars orbiting a central mass. But galaxies behave differently. It is as if the string never gets longer, as if invisible mass extends far beyond the visible edge. Gravitational lensing provides even more striking evidence. Massive objects bend light, distorting images of distant galaxies behind them. When astronomers measure how much bending occurs, they find far more mass than what telescopes can see. In some cases, like the Bullet cluster, the separation between visible matter and gravitational mass is dramatic. Two galaxy clusters collided, and the hot gas slowed down and piled up in the center. But gravitational lensing showed that most of the mass passed straight through, behaving as if it were invisible and collisionless. This observation is difficult to explain without dark matter. Modified gravity theories struggle to account for such clean separations. Yet dark matter itself remains mysterious. It does not emit light, absorb light, or reflect light. It interacts gravitationally, but barely, if at all, through other forces. Numerous experiments have attempted to detect dark matter particles directly, using underground detectors shielded from cosmic radiation. So far, none have produced conclusive results. Particle accelerators have also searched for dark matter signatures, again without definitive success. This has led some physicists to question whether dark matter exists at all, or whether gravity behaves differently on large scales. Modified Newtonian dynamics, or MOND, proposes that gravity changes behavior when accelerations become extremely small. Instead of weakening indefinitely, gravity transitions to a different regime. MOND can explain galaxy rotation curves surprisingly well with fewer assumptions, but it struggles with galaxy clusters, gravitational lensing, and cosmology. Other modified gravity theories attempt to build relativistic versions of MOND, adjusting spacetime geometry itself. These theories can be mathematically complex and often introduce new fields or parameters. So far, no alternative theory has matched the explanatory power of dark matter across all scales. But the very need to invoke dark matter hints at our incomplete understanding of gravity. It is possible that dark matter exists, but it is also possible that gravity is subtly different from what we expect. The same tension appears when we examine the universe on the largest scales of all. The expansion of the universe is accelerating. This was discovered in the late 1990s through observations of distant supernovae. Gravity, as an attractive force, should slow cosmic expansion, but instead, the expansion speeds up. To explain this, physicists introduced dark energy, a mysterious component that permeates space and exerts a repulsive effect. Dark energy appears to make up about 70% of the universe's total energy content. Ordinary matter accounts for less than 5%. Dark matter contributes about 25%. In other words, everything we can see, touch, and directly detect is a tiny minority of the cosmic budget. Dark energy behaves like a property of space itself. As space expands, more dark energy appears. This is counterintuitive, because energy conservation seems violated. But in general relativity, energy conservation is more subtle. Expanding space can carry energy without a clear source. One way to think about dark energy is to imagine space as a stretched rubber sheet that resists compression. As it expands, the tension grows. Another analogy is vacuum pressure. Even empty space is not truly empty. Quantum fields fluctuate constantly, creating transient particles and energy. The energy of these fluctuations could act like dark energy. But theoretical calculations overshoot observed values by an enormous factor, making this explanation deeply unsatisfying. Once again, gravity sits at the center of the mystery. Dark energy might not be a new substance. It might be a sign that gravity behaves differently on cosmic scales. Some theories propose that gravity leaks into extra dimensions, weakening its pull over large distances. Others suggest that space-time geometry changes over time. There are even proposals where dark energy and dark matter emerge from the same underlying physics, linked to space-time microstructure. What makes all of this more unsettling is how well general relativity works in many other contexts. It predicts gravitational waves, black hole mergers, and time dilation with astonishing accuracy. The theory has passed every test thrown at it, yet still appears incomplete. This creates a strange situation. Gravity is both one of the most successful and most mysterious ideas in physics. It works beautifully where we can test it directly. It fails where we need it most. This duality suggests that gravity may not be wrong, but unfinished. Cosmic structure formation provides another clue. The universe did not always look the way it does now. Early on, matter was nearly uniform. Tiny fluctuations grew under gravity, forming filaments, clusters, and voids. Simulations that include dark matter reproduce this structure remarkably well. Without dark matter, galaxies would not have formed quickly enough. This success strengthens the dark matter hypothesis, but it does not eliminate the possibility that gravity itself is doing something unexpected. It is possible that what we call dark matter is actually a manifestation of gravitational physics we do not yet understand. Some theories propose that inertia itself emerges from interactions with the vacuum, altering how objects respond to gravity. Others explore entropic gravity, where gravity arises from statistical tendencies rather than fundamental forces. In such models, gravity is not something objects generate. It is something systems tend toward. While these ideas remain controversial, they highlight an important shift. Gravity may not be a force in the traditional sense. It may be a consequence. The question then becomes, a consequence of what? Information, geometry, quantum entanglement, higher dimensions? Each answer leads to a different picture of reality. What is clear is that gravity is not simply a weaker version of other forces. It plays by different rules. It shapes time, space, and causality. It connects the smallest scales to the largest. Understanding gravity may require rethinking what it means for something to exist, to interact, to move. As we approach the final parts, we will explore how gravity influences the fate of the universe, how it may connect to the arrow of time, and why solving the mystery of gravity could reshape not just physics, but our understanding of reality itself. If gravity truly holds the key to the universe's deepest structure, then its influence must extend not only across space, but across time itself. And this is where gravity quietly reshapes one of the most puzzling ideas in all of science: why time has a direction at all. At the level of fundamental physics, most equations do not care which way time flows. If you filmed atoms colliding and played the video backward, the motion would still obey the same laws. Yet our experience of time is unmistakably one way. Eggs break, but do not unbreak. Heat spreads out, but does not spontaneously concentrate. Memories form of the past, not the future. This asymmetry is known as the arrow of time, and gravity may be one of the main reasons it exists. The connection begins with entropy, a measure of disorder. The second law of thermodynamics states that entropy tends to increase over time. Systems move from ordered states to disordered ones. At first glance, gravity seems to contradict this. Gravity pulls matter together, creating stars, planets, and galaxies. That looks like order increasing, not decreasing. But gravity plays a subtle trick. When matter clumps under gravity, entropy actually increases overall. The system releases energy, forms structures, and opens up many more possible microscopic configurations. A uniform gas has fewer ways to arrange itself than a complex system of stars and radiation. In this sense, gravity accelerates entropy growth by allowing matter to collapse and release energy. This means gravity may be responsible for giving time its direction, at least on cosmic scales. But that only deepens the mystery. If gravity increases entropy, why did the universe begin in such an extraordinarily low entropy state? The early universe was incredibly smooth, uniform, and simple. Matter was evenly distributed. There were no stars, no galaxies, no black holes. From an entropy perspective, this is astonishingly special. There were vastly more disordered configurations available. So why did the universe start out so orderly? Physicist Roger Penrose famously calculated the odds. The initial state of the universe appears to have been tuned to 1 part in 10^10 1023. That number is so large it defies intuition. It suggests that the low entropy beginning of the universe is not an accident. It demands explanation. This is where gravity becomes even more intriguing. In ordinary systems, maximum entropy corresponds to uniformity. But for gravity, the opposite is true. The highest entropy gravitational state is not smoothness, but clumping. Ultimately, the highest entropy state for a gravitating system is a collection of black holes. Black holes, it turns out, are entropy monsters. They contain enormous entropy proportional to the area of their event horizons. A single supermassive black hole contains more entropy than all the stars and gas in a galaxy combined. If entropy drives time forward, then black holes are the ultimate sinks of time's arrow. This suggests that the universe began far from gravitational equilibrium. Gravity had not yet had time to clump matter. In that sense, the low entropy of the early universe may be explained by gravity simply not having done its work yet. But that explanation raises another question. Why was gravity initially unable to clump matter? One possibility is that the geometry of spacetime itself began in a special configuration. General relativity allows many possible spacetime geometries. Some are chaotic, others are smooth. The universe may have begun in a geometrically simple state, one that suppressed gravitational degrees of freedom. In this view, gravity did not start off weak or inactive. It started off constrained. As the universe expanded, these constraints relaxed. Gravity gained freedom. Structure formation began. Time's arrow emerged as gravity gradually unlocked more and more possible configurations. This paints a picture of time not as something fundamental, but as something that emerges from gravitational evolution. Some physicists have taken this idea further, suggesting that time itself may not exist at the deepest level of reality. In quantum gravity, especially in approaches like the Wheeler-DeWitt equation, time disappears from the equations entirely. The universe is described as a static wave function, containing all possible configurations at once. From this perspective, time arises only when observers within the universe compare states and notice changes. Gravity, in shaping spacetime geometry, may be responsible for creating the illusion of temporal flow. Another way to see this is through black holes. Inside a black hole, time and space swap roles. Moving forward in time inevitably leads toward the singularity, just as moving forward in space leads outward in ordinary situations. This strange behavior suggests that time is deeply tied to spacetime structure, not an independent background parameter, and gravity is what shapes spacetime. Even outside black holes, gravity affects time. Clocks tick more slowly in stronger gravitational fields. GPS satellites must correct for this effect to function properly. Time literally flows at different rates depending on gravity. This is not a philosophical idea. It is a measurable physical fact. When gravity bends space-time, it bends time itself. This raises a provocative possibility. Perhaps gravity does not act within time. Perhaps time emerges from gravity. If that is true, then understanding gravity fully may require abandoning our intuitive notion of time as something fundamental. The universe may be more like a vast network of relationships than a sequence of moments. Some modern theories suggest that space-time emerges from quantum entanglement. Regions of space that are strongly entangled are close together. regions with weak entanglement are far apart. In these models, gravity arises from changes in entanglement structure. Time, then, could be the process by which entanglement patterns evolve. This would make gravity, space, and time all aspects of the same underlying phenomenon. Another angle comes from cosmology. As the universe expands, gravity shapes the formation of large-scale structures. This creates a cosmic arrow of time, independent of local thermodynamic arrows. Galaxies form, stars age, black holes grow. These processes define a direction in which the universe evolves. Even if local physics were time-symmetric, the global structure of the universe would not be. Gravity is the agent driving that global evolution. This also ties into the ultimate fate of the universe. If dark energy continues to dominate, the universe may expand forever. Galaxies will drift apart. Stars will burn out. Black holes will slowly evaporate. In this scenario, gravity gradually loses its ability to create new structure. Entropy reaches a maximum. Time effectively comes to an end. If instead the universe recollapses, gravity would reverse the expansion. But even then, entropy would continue to increase, preventing a true reversal of time. Either way, gravity defines the long-term narrative. What makes gravity so difficult to understand is that it operates at every level of reality. It governs the fall of an apple, the orbit of planets, the birth of stars, the evolution of galaxies, the expansion of the universe, and possibly the emergence of time itself. Yet we still do not know what gravity is. Is it a force, a curvature, an emergent phenomenon, a statistical tendency? Perhaps it is all of these, depending on the scale. The deeper we look, the more gravity seems less like a thing and more like a relationship. It connects mass and energy to geometry. It connects space to time. It connects order to disorder. Understanding gravity may require letting go of the idea that the universe is built from objects interacting through forces. Instead, the universe may be built from structure, information, and relationships, with gravity as the glue that holds it together. In the next and final parts, we will explore how gravity influences the ultimate fate of the universe, how it may unify with other forces, and why solving gravity's mystery could transform not only physics, but our understanding of reality itself. If gravity helps shape time, structure, and the large-scale story of the universe, then the next natural question is whether gravity is truly fundamental, or whether it is something that emerges from deeper rules we have yet to fully uncover. This question sits at the heart of modern theoretical physics, and it is one of the reasons gravity remains so stubbornly mysterious. For more than a century, general relativity has described gravity as the curvature of spacetime caused by mass and energy. This picture works astonishingly well on large scales. It predicts the motion of planets, the bending of light around galaxies, the expansion of the universe, and the existence of black holes. Every experimental test so far has confirmed its predictions with incredible precision. But when we zoom in to the smallest scales, the picture begins to crack. At the level of atoms and particles, the universe is governed by quantum mechanics. This framework describes reality not as smooth and continuous, but as probabilistic and discrete. Energy comes in packets. Fields fluctuate. Particles appear and disappear. General relativity, on the other hand, assumes spacetime is smooth and continuous, like a perfectly stretched fabric. Trying to combine these two pictures has proven extraordinarily difficult. When physicists attempt to quantize gravity in the same way they quantize other forces, the equations explode into infinities that cannot be removed. This tells us something important. Gravity may not behave like the other forces at the deepest level. One way to think about this is through analogy. Imagine trying to describe traffic flow using the laws of fluid dynamics. On large scales, cars behave like a flowing liquid. But zoom in close enough, and the illusion breaks. Cars are discrete objects with drivers making decisions. The fluid description fails. Gravity may be like traffic flow. On large scales, it looks smooth and geometric. On small scales, it may emerge from something else entirely. This idea has gained traction in recent decades. Some physicists now suspect that gravity is not fundamental, but emergent, like temperature or pressure. Temperature feels fundamental, but it is really just a measure of the average motion of many particles. Pressure is not a force by itself, but a statistical effect of countless collisions. Gravity may be similar. It could arise from the collective behavior of microscopic degrees of freedom we do not yet understand. One compelling proposal along these lines comes from the study of black hole thermodynamics. In the 1970s, physicists discovered that black holes behave like thermodynamic objects. They have temperature. They have entropy. They obey laws remarkably similar to the laws of thermodynamics. This was shocking. Black holes were once thought to be simple objects defined only by mass, charge, and spin. The fact that black holes possess entropy suggests they have hidden microscopic states. And where there is entropy, there are underlying degrees of freedom. This hints that spacetime itself may have microscopic building blocks. If spacetime has atoms, then gravity could be the macroscopic behavior of those atoms. Another clue comes from the holographic principle. This idea, inspired by black hole physics and later formalized in string theory, suggests that all the information inside a region of space can be described by data on its boundary. In other words, the universe may be like a hologram, where a lower dimensional surface encodes a higher dimensional reality. In certain models, gravity emerges naturally from the behavior of quantum systems living on the boundary. This has been made precise in a framework called ADS-CFT correspondence, where gravitational theory in one space is equivalent to a quantum theory without gravity in another. Although our universe does not exactly match this setup, it strongly suggests that gravity can emerge from quantum information. This leads to an extraordinary possibility. Gravity may be a consequence of information trying to organize itself. Some researchers have proposed that gravity arises from changes in entropy associated with the position of matter. When matter moves, the amount of information associated with space-time changes, and gravity appears as an entropic force. This idea, proposed by physicist Eric Verlande, reframes gravity not as a fundamental interaction, but as a tendency of systems to maximize entropy. In this picture, gravity is like the tension that emerges when you stretch a rubber band. It is not fundamental, it arises from the underlying molecular structure. Whether this specific model is correct remains debated, but the broader idea, that gravity is emergent, is gaining support. Another area where gravity's mystery deepens is in the context of dark matter and dark energy. Galaxies rotate faster than expected based on visible matter. The expansion of the universe is accelerating. These phenomena are usually explained by invoking unseen components that dominate the universe's mass-energy budget. But an alternative approach suggests that gravity itself may behave differently on large scales. Modified gravity theories propose that general relativity breaks down in subtle ways at galactic or cosmic distances. These theories attempt to explain observations without dark matter or dark energy by changing how gravity works. While none have yet replaced the standard model of cosmology, their existence highlights how little we truly know about gravity's behavior across scales. What makes gravity especially puzzling is its weakness. Compared to the other forces, gravity is extraordinarily feeble. A small magnet can lift a paperclip against the gravitational pull of the entire Earth. Why is gravity so weak? One possibility is that gravity leaks into extra dimensions. In some theories, gravity spreads out across higher dimensional space, diluting its strength in our familiar 3 dimensions. Another possibility is that gravity's weakness reflects its emergent nature. It may not be a force at all, but a residual effect of deeper dynamics. The mystery deepens when we consider quantum vacuum energy. Quantum field theory predicts enormous energy in empty space. This energy should gravitate, causing spacetime to curve violently. But observations show that the vacuum energy density is incredibly small. This discrepancy, known as the cosmological constant problem, is one of the biggest unsolved problems in physics. It suggests that our understanding of how gravity interacts with energy is incomplete. Some physicists suspect that gravity somehow ignores most vacuum energy, or that space-time adjusts itself dynamically. Either way, gravity does not behave the way we expect. All of this paints a picture of gravity as a messenger from deeper layers of reality. It is telling us that space, time, matter, and energy are not fundamental ingredients, but emergent features of something more basic. Gravity may be the shadow cast by that deeper structure. If so, then solving the mystery of gravity could reveal the true architecture of the universe. It could explain why space-time exists at all, why the laws of physics take the form they do, and why the universe evolves the way it does. This is why gravity sits at the center of so many unsolved questions. It connects the smallest scales to the largest. It links information to geometry. It ties together time, entropy, and cosmology. And yet, we still lack a complete theory that unites gravity with quantum mechanics. The search for quantum gravity is not just about unifying equations. It is about understanding what reality is made of. In the next part, we will explore how gravity governs the birth and death of the universe itself, from the Big Bang to its possible endings, and why gravity may determine whether the cosmos lives forever, tears itself apart, or quietly fades into darkness. If gravity may emerge from deeper laws, then its role in shaping the ultimate fate of the universe becomes even more intriguing. Gravity is not just the force that pulls objects together. On cosmic scales, it acts like a storyteller, quietly deciding how the universe begins, evolves, and possibly ends. To understand this, we need to zoom out to the largest canvas imaginable. The universe began in a state where gravity played a paradoxical role. In the earliest moments after the Big Bang, everything was incredibly dense and hot. Gravity should have pulled everything back together instantly. Yet instead, space expanded. This tells us that gravity is not always attractive in the way we experience it locally. When energy dominates in certain forms, gravity can effectively push space apart. During a brief period called cosmic inflation, space-time expanded exponentially fast. Regions that were once subatomic in size ballooned to cosmic scales in a fraction of a second. This expansion smoothed out irregularities and set the stage for the large-scale structure we see today. Gravity then switched roles. As the universe cooled and matter formed, gravity became the architect of structure. Tiny fluctuations in density, barely 1 part in 100,000, grew under gravity's influence. Over billions of years, these fluctuations became galaxies, clusters, and vast filaments stretching across space. An easy way to picture this is to imagine a calm lake with tiny ripples. Gravity acts like a slow but persistent current, amplifying some ripples while dampening others until patterns emerge. Without gravity, the universe would be a thin, boring fog. But gravity also has limits. As galaxies formed, gravity pulled matter inward, but something resisted complete collapse. Stars ignited nuclear fusion, generating outward pressure. This balance between gravity pulling in and energy pushing out defined the lifetimes of stars. Eventually, gravity won. Stars ran out of fuel. Massive ones collapsed into black holes. Smaller ones became white dwarfs or neutron stars. Gravity compressed matter to extraordinary densities, bending space-time so severely that even light could not escape. On these scales, gravity is brutal and uncompromising. But on the largest scales of all, gravity seems to be losing. In the late 1990s, astronomers discovered that the expansion of the universe is accelerating. Galaxies are not just moving away from each other. They are doing so faster and faster. This implies the presence of a mysterious component called dark energy. Dark energy behaves like a kind of negative pressure built into space itself. Instead of pulling matter together, it pushes space apart. In terms of gravity, dark energy acts like anti-gravity on cosmic scales. This creates a profound tension. Gravity wants to clump matter together. Dark energy wants to tear the universe apart. Which one wins determines the fate of everything. If gravity were stronger relative to dark energy, the expansion might slow, stop, and reverse. The universe would collapse in a big crunch, compressing all matter back into a hot, dense state. If dark energy remains constant or grows stronger, the universe will expand forever. Galaxies will drift apart. Stars will burn out. Black holes will evaporate. The universe will approach a cold, empty state known as heat death. There is even a more extreme possibility. If dark energy increases over time, it could lead to a big rip. In this scenario, the expansion becomes so violent that galaxies, stars, planets, and eventually atoms are torn apart. Gravity would lose at every scale. These scenarios show that gravity is not just a local force. It is a global influence shaping the entire destiny of the cosmos. What makes this especially unsettling is that gravity's role in cosmic evolution depends on things we barely understand. We do not know what dark energy is. We do not know why its density is so small yet so dominant. We do not know whether gravity changes behavior over vast distances or times. Even worse, we do not know whether gravity itself evolves. Some theories suggest that gravity was stronger or weaker in the past. Others propose that its behavior depends on the structure of space-time itself. If gravity is emergent, then its strength and form may depend on cosmic conditions. This opens the door to radical possibilities. Perhaps the laws of gravity are not fixed, but statistical. Perhaps they arise from deeper rules that only appear stable over long timescales. Perhaps what we call gravity is just the low-energy approximation of a much richer phenomenon. This perspective changes how we think about cosmic beginnings. The Big Bang may not have been the beginning of everything, but a transition between phases. Gravity may have behaved differently before it. Some models suggest that the universe could have bounced from a previous contraction. Others propose cyclic universes, where gravity drives repeated expansions and collapses. In these scenarios, gravity is not just a force, it is the rhythm of cosmic history. There is also the question of gravitational entropy. Entropy usually increases over time, but gravity complicates this picture. Gravitational systems can become more ordered as they evolve, forming stars and galaxies. This apparent contradiction is resolved by realizing that gravity stores entropy in spacetime itself, especially in black holes. Black holes may represent the maximum entropy states allowed by gravity. If so, the universe's long-term evolution may be governed by how gravity redistributes entropy across spacetime. This connects gravity to the arrow of time. Time seems to flow in one direction because entropy increases. Gravity plays a central role in determining how entropy grows on cosmic scales. In a universe dominated by dark energy, entropy will continue increasing as matter disperses and black holes evaporate. In a collapsing universe, entropy may reach a maximum at the Big Crunch. Either way, gravity helps define what past and future mean. Another unsettling implication is that gravity may limit what we can ever observe. As the universe expands faster, distant regions slip beyond our cosmic horizon. Their light will never reach us. Gravity and expansion together define the observable universe. This means that much of the cosmos is already forever hidden. In the far future, observers in our galaxy may see only a small island of stars surrounded by darkness. Evidence of the Big Bang itself could fade from view. Gravity will have quietly erased our ability to reconstruct cosmic history. This raises philosophical questions as well as scientific ones. Are the laws of gravity universal, or are they conditioned by our cosmic environment? Is our understanding of gravity biased by living at a particular time in cosmic history? Could civilizations in other eras infer different laws? These questions remind us that gravity is not just a technical problem. It shapes what can be known. It determines which signals reach us, which structures form, and which questions can be answered. As we approach the final part, the mystery becomes clear. Gravity is deeply familiar and profoundly alien. It governs falling apples and orbiting planets, yet also dictates the fate of galaxies and the universe itself. We use it every day without thinking, yet it resists every attempt at complete understanding. In the final part, we will step back and ask what gravity ultimately teaches us, not just about the universe, but about the limits of knowledge, the nature of reality, and why this most ordinary force may be the deepest clue we have about how everything fits together. When we step back from equations, telescopes, and thought experiments, gravity leaves us with something both unsettling and strangely reassuring. It is the force we first experience as children, long before we understand words like mass or space-time. We learn gravity by falling, by dropping toys, by watching rain hit the ground. It feels obvious, almost boring. And yet, after centuries of science, gravity remains the least understood of all fundamental forces. This contrast is not accidental. Gravity sits at a crossroads between the everyday world and the deepest structure of reality. On one side, it governs motion we can see and feel. On the other, it shapes black holes, warps time, and determines the fate of the universe. No other force operates so gently at small scales and so decisively at large ones. One reason gravity is so hard to fully grasp is that it refuses to fit neatly into our existing frameworks. Quantum mechanics describes the microscopic world with astonishing precision, yet it struggles to accommodate gravity. General relativity explains gravity as geometry, but it breaks down at the smallest scales. This mismatch is not just a technical inconvenience. It suggests that our understanding of reality is incomplete. Every attempt to unify gravity with quantum theory forces us to confront uncomfortable possibilities. Space and time may not be fundamental. Reality may be discrete rather than continuous. Cause and effect may not operate the way we assume. In trying to understand gravity, we are forced to question the very stage on which physics plays out. What makes gravity especially intriguing is that it may not be a force in the usual sense at all. If gravity is emergent, then it is more like temperature than electricity. Temperature feels fundamental, but it emerges from the collective motion of particles. No single atom has a temperature. Gravity may work the same way. Spacetime curvature could arise from microscopic degrees of freedom we have not yet identified. Black hole entropy hints at hidden layers of information encoded on surfaces, not volumes. The universe may be governed by principles that prioritize information, not matter. If this is true, gravity is not something added to reality. It is something reality does. This perspective changes how we think about cosmic origins. The Big Bang may not mark the creation of space and time, but a phase transition in a deeper system. Gravity may have emerged as the universe cooled, much like ice crystallizes from water. Even the expansion of the universe takes on new meaning. Instead of space stretching like rubber, it may reflect changes in the underlying informational structure of reality. Dark energy might not be a mysterious substance, but a property of space-time itself. These ideas are speculative, but they are guided by evidence, not imagination alone. Observations of gravitational waves confirm that space-time is dynamic. Precision cosmology reveals tensions in how gravity behaves across scales. Black hole physics consistently points toward deeper principles. Gravity keeps whispering that there is more beneath the surface. At the same time, gravity humbles us. It sets limits on what we can observe, measure, and know. Event horizons hide information. Cosmic expansion hides distant regions forever. Singularities challenge the applicability of our laws. Gravity does not just shape the universe, it shapes the boundaries of knowledge. This may be its most profound role. Every scientific theory depends on assumptions about space, time, and causality. Gravity governs all three. Any theory of everything must pass through gravity, not around it. And yet, gravity also connects us. The same force that curves space-time around black holes keeps the moon in orbit, holds Earth together, and keeps us grounded as we walk. The laws that govern distant galaxies also apply beneath our feet. In that sense, gravity is a bridge between the cosmic and the familiar. It reminds us that we are not separate from the universe we study. We are embedded within it, shaped by the same forces we try to understand. As science advances, gravity continues to guide progress in unexpected ways. Gravitational wave astronomy has opened a new window on the universe. Precision measurements of spacetime test fundamental physics. The search for quantum gravity pushes theory toward new conceptual territory. Each discovery raises new questions. Why does gravity have the strength it does? Why does it couple to energy and momentum the way it does? Why does spacetime have the dimensions it has? We do not yet know the answers. But gravity has taught us something crucial already. Reality is deeper than it appears. The most familiar aspects of the universe may be clues, not conclusions. The force we take for granted may be the doorway to the most radical insights. In the end, gravity is not just a problem to be solved, it is an invitation to rethink space and time, an invitation to explore the limits of knowledge, an invitation to accept that the universe may be stranger, richer, and more subtle than we ever imagined. And perhaps that is why gravity, despite centuries of study, still feels unfinished. It is not meant to be easily mastered. It is meant to keep us asking better questions. Because in trying to understand gravity, we are really trying to understand how reality holds itself together, and why it does so at all. And that may be the most fundamental question science has ever asked.